Baik, Bapak dan Ibu, akan kita mulai acara webinar pada siang hari ini. Bismillahirrahmanirrahim. Assalamualaikum warahmatullahi wabarakatuh. Selamat siang dan salam sejahtera untuk kita semua. Yang saya hormati dan saya muliakan Bapak Insinyur Ali Iskandar, STMT, selaku Wakil Sekretaris 2 HATTI, Himpunan Ahli Teknik Tanah Indonesia, our respected Mr. Sing Chen and Miss Jamie Howe from Bentley Systems. Yang saya hormati dan saya muliakan Bapak, Ibu, seluruh peserta webinar. Alhamdulillah, tentunya pertama-tama kita panjatkan puji dan syukur atas kehadirat Allah Subhanahu wa Ta'ala, karena berkat dan karunia Allah Ta'ala semata acara webinar kita dapat diselenggarakan. Terima kasih yang sebesar-besarnya kami haturkan kepada HATTI, Himpunan Ahli Teknik Tanah Indonesia, yang telah berkenan berkolaborasi dengan Kurnia Handasa Nevada. Tentunya ini merupakan suatu kehormatan dan kebanggaan bagi kami. Bapak dan Ibu yang saya hormati, perkenalkan, nama saya Nesi dari PT Kurnia Handasa Nevada. Sekilas tentang kami, Kurnia Handasa Nevada adalah Authorized Bentley Partner Indonesia, Authorized Partner untuk penjualan software-software Bentley di Indonesia. Salah satu software dari sekian banyak software yang dimiliki Bentley adalah PLAXIS. Tema webinar kita hari ini adalah Excavation and Temporary Shoring Design using PLAXIS. Deformasi merupakan salah satu kriteria penting dalam proyek galian, dan besarnya pergerakan tanah sangat tergantung pada tahapan pelaksanaan galian serta sistem penahan tanah shoring yang digunakan. Sesi ini akan mendemonstrasikan alur kerja modeling workflow dari suatu permasalahan galian. Semoga acara webinar ini dapat berkontribusi dan memberikan manfaat kepada anggota HATTI, sehingga hubungan kerjasama yang baik antara Kurnia Handasa Nevada dan HATTI dapat terjalin berkelanjutan. Acara webinar kita pada hari ini akan dibuka dengan sambutan yang saya hormati dan saya muliakan Bapak Insinyur Ali Iskandar, STMT, selaku Wakil Sekretaris 2 HATTI. Kepada yang terhormat Bapak Ali Iskandar, kami persilahkan. Silakan Bapak, open mic.
Baik Ibu, apakah sudah terdengar suara saya?
Terdengar Pak, terdengar. Terima kasih.
Oke, langsung dimulai ya Bu.
Ya Pak.
Ya. Oke. Selamat siang Bapak dan Ibu, rekan-rekan semua. Salam sejahtera untuk semua. Perkenalkan, nama saya Ali Iskandar dari DPP HATTI. Terima kasih atas kehadirannya dalam webinar hari ini dengan topik Excavation and Temporary Shoring Design using PLAXIS. Saya mewakili Ketua Umum kami, Himpunan Ahli Teknik Tanah Indonesia, Prof. Wijoyo, yang berhalangan hadir untuk menyampaikan salam hangat serta apresiasi atas partisipasi Bapak dan Ibu sekalian. Topik yang kita bahas hari ini tentunya sangat relevan dengan praktek geoteknik modern, khususnya dalam memahami deformasi tanah dan pentingnya tahapan konstruksi pada pekerjaan galian serta sistem penahan sementara. Dalam geoteknik, tahapan konstruksi bukan sekedar urutan pekerjaan, tetapi bagian dari perilaku sistem itu sendiri, baik untuk galian, timbunan, dan lain-lain. Tanah akan merespon adanya perubahan beban, perubahan kondisi batas, dan perubahan tekanan air pori secara bertahap. Karena itu banyak kegagalan geoteknik itu justru terjadi saat proses konstruksi berlangsung, yaitu ketika sistem belum sepenuhnya terbentuk secara baik atau belum mencapai kondisi stabil atau akibat stage yang tertukar. Ini berbeda dengan banyak kasus pada struktur di mana analisis umumnya difokuskan pada kondisi akhir saja. Dalam geoteknik, kondisi sementara bisa menjadi kondisi yang paling kritis atau menentukan. Oleh karena itu, memahami tahapan pelaksanaan bukan hanya penting, tapi sangat fundamental dalam perancangan yang aman dan handal. Akhir kata, kami mengucapkan terima kasih kepada para narasumber, Miss Jamie Ho dan Mr. Xing Cheng Lin yang telah berkenan berbagi pengetahuan dan pengalaman, serta kepada seluruh pihak yang telah mendukung terselenggaranya acara ini. Semoga webinar ini berjalan lancar, bermanfaat, dan memberi nilai tambah bagi kita semua. Dengan demikian, acara webinar hari ini saya resmi nyatakan dibuka. Terima kasih, selamat mengikuti sesi dan semoga diskusinya produktif.
Terima kasih kepada Bapak Ali atas sambutan yang telah diberikan. Selanjutnya kita akan memasuki sesi materi pertama yang akan dibawakan oleh Miss Jamie Howe as Product Sales Engineer from Bentley Systems yang akan memaparkan pengenalan produk geoteknik dari Bentley. Kepada Miss Jamie kami persilakan. Miss Jamie, the floor is yours.
Thank you, Bu. Thank you, Pak Ali, as well. And thank you, everyone. Good day to all of you again. And thank you so much for your time in joining us in today's session. So allow me to share my screen here. Do let me know if you can see my screen. Can you see anything? All
yes,
good?
we can see.
Okay.
Yeah.
Thank you. Thank you. So once again, thank you for joining us today in our webinar entitled Excavation and Temporary Shoring Design Using PLAXIS. And thank you as well to Bu Nessie, PT Kurnia, Handasa, Nevada, and HATTI for co-jointly organizing this event. And once again, thank you all of you. We hope you find today's event fruitful for you in your projects as well. And if you have any questions, do feel free to let us know. You can put it in the chat or you can ask us at the end of the session later. So before we move on to the technical session, I'm just going to give an overview of our Bentley Geotechnical Engineering Solutions. Firstly, by introducing all of you to Bentley Systems, what we are, our Geotechnical Engineering Solutions, and a Virtuosity Practitioner license. So for Bentley Systems, we are an infrastructure engineering software company. We were established in 1984. So we have been in the industry for more than 40 years now. And we provide innovative software to help all of you, engineers and organizations, to better design, build, and operate all your projects. And Bentley Systems, we also help all of you. We have users in more than 190 countries globally. We are also listed in NASDAQ, which is one of the world's major stock exchanges. So being a global software company, we provide comprehensive engineering solutions in various industries, from architecture, engineering, construction, and operations. This software is useful for your projects throughout the whole life cycle of your project, as shown in this slide here. Let me get the pointer. Yeah, as shown here. So for geotechnical engineering, it is in the design and engineering portion of the project life cycle. So in most of the solutions, what we can see are the above ground solutions in the built world, where we can see it easily because they are all constructed above ground. So we also have a group of solutions which covers the underground, whatever that is in the subsurface world under the sequence group. So that is grouped under the Bentley Geotechnical Engineering Solutions, and it comes in three main categories as shown here: geotechnical information management, geotechnical modeling, and geotechnical analysis. So for geotechnical information management, we have open ground for you to manage and consolidate all your subsurface information, so that you can all refer from one single source of truth, from all the way from site, after lab test, and to the designer as well. And then for geotechnical modeling, we have leapfrog works, which you can use to model the subsurface geological profile for you to make better decisions because you can visualize what is underneath more easily. So this can help you save time in decision making as well. And lastly, in terms of geotechnical analysis, we have PLAXIS and GeoStudio. And today we have our focus will be on PLAXIS, which is the finite element solution, and GeoStudio is our limit equilibrium solution for slope stability analysis purpose. And this slide here shows the life cycle or the workflow of geotechnical work for any particular project. So in terms of geotechnical work, we always start with site investigation work. So this is where open ground comes into the picture, where you can save and consolidate all the subsurface data into one database and to be used in the future, whether it's for modeling through leapfrog works or for your analysis work through PLAXIS or GeoStudio. So in terms of geotechnical analysis, it covers many different types of work, all the way from offshore to nearshore to upstream like dams and to on ground as well for buildings, for utilities, infrastructures like roads, rails, underground tunnels, for mining work, and also for infrastructures like airports as well. So geotechnical work covers a huge work scope because anything that we construct is either on ground or underground. So we always need to assess what is the impact of the structure and the loads from those structures or utilities and how they react, how the ground react to them. So this is where geotechnical analysis comes into the picture. So in terms of PLAXIS, it comes in 3 different products, 2D, 3D, and monopile designer. PLAXIS monopile designer is for laterally loaded monopile design. This is mainly for offshore wind farms where we have single large diameter piles for the wind turbines. And PLAXIS 2D and 3D, they each come in 3 different product tiers, as you can see here. The lowest tier is called just 2D and 3D. Then we have the advanced tier, and we also have the ultimate tier. And this slide here shows a simplified comparison between the 3 product tiers of PLAXIS 2D and PLAXIS 3D. So for very basic analysis, just plastic and safety analysis, you can always go for the lowest product tier. And if you require anything more, such as consolidation, steady state, groundwater flow, creep pseudostatic analysis, and degradation of soil due to cyclic loading, then you will require at least the advanced tier. And for the ultimate tier, this is the highest tier. So if you require more advanced analysis like transient groundwater load, transient loadings like vibrations, traffic load, liquefaction, seismic load, then you will require the ultimate tier. And if you are designing to Eurocode, and where you need to have input of the design approaches and the partial factors, then you require at least the advanced tier. So today's topic is on excavation and shoring. This is just an illustration or an image of how usually it is done in PLAXIS. This shows here in 2D. And if for more complex cases where you need to do more of an overall assessment of the whole system, then probably 3D is the solution for you to go for. One example that we have here is the reconstruction of the Palu Bridge in Indonesia. This was done by PT Wijaya Karya. In this case, as you can see here, PLAXIS is used for the excavation check of this temporary shoring of the bridge foundation. And next, we move on to just a quick introduction to Virtuosity Practitioner License. So Virtuoso subscription is a flexible subscription. It can be purchased by any entity, whether you are from a very huge entity or just an individual, anyone can purchase it. This subscription is also very flexible. It's only for 12 months. There is no commitment for you to renew your subscription. So if you're only getting a project, say for 2-3 years, and you only need to use software for 2-3 years, then this is a solution for you because you can just use it, and then after that you can just let it expire. And when you have a new project later, you can purchase a new subscription again. And another common thing that users like about this subscription is the keys that come bundled with the license. Keys are like tokens or credits that users can redeem when they purchase a license. So for example, if you purchase a PLAXIS license for Virtuoso, it comes bundled with keys, which helps you unlock different types of free trainings. All these trainings are online, and it can be standard training or it can be customizable to your team's requirement. Just an example, for example, if you purchase the software today, payment is made, and let's say tomorrow the license is delivered to you, then within 2 to 3 days from the delivery of license, our technical team will be in touch with your team. And then you can then discuss on your training requirements, how you can utilize the keys to carry out training for your team. It can be a standard recorded training as shown here. If you want to learn just the basic workflow and all, there is a recording that you can watch. You can watch it as many times as you want whenever you are free to watch it for a period of 90 days. Other than that, we also have the live training through Microsoft Teams with our technical experts. So that the content of the training can be customizable to what your team wants to learn about. Let's say if you purchase PLAXIS just for an excavation project and you're not too confident in it yet, you can always discuss with our team and they will work out a module that is suitable for you using the keys utilization. The number of keys that come bundled with a license also different depending on what product that you purchase. So for the lowest product tier of PLAXIS Studio, it comes with 1 key per license. And for the rest of the PLAXIS products, 2 keys per license. So 1 key is almost 2 hours of free training that you can redeem. So in summary, Virtuoso Practitioner license is a name user license. It is a yearly investment because there is no additional maintenance fee to pay and there is no commitment for you to renew every year. So with this, you can have full control over your yearly software costs for your project. And throughout your whole active subscription period, you can get support, technical support through ticket submission. And if there's any new release of the software, you can download the software for free as well, the latest version for free throughout your active subscription period. And lastly, we have the expert services using keys, which we have explained earlier, for you to redeem free trainings for your team. And if you need any further information, do reach out to Bu Nessie or PT Kurnia Handasa Nevada. As mentioned by Bu Nessie just now, they are our channel partner in one of our channel partners in Indonesia, and they will be assisting you further on any inquiries that you have. So with that, thank you so much. I'll hand it back over to Bu Nessie. Thank you.
Thank you very much, Ms. Jamie, for your insightful presentation. Now we will move on to our main session delivered by our keynote speaker, Mr. Sing Chen Lin, as Senior Product Success Manager of Bentley System. Mr. Sing Chen, now the floor is yours.
Good afternoon. Am I audible?
Good afternoon. Yes,
Yes,
we can hear you.
We can hear you.
That's good. All right. So thank you so much for invitation from Kurnia Handasa for this webinar. And thank you, HATTI. So I'm about to share my screen. So let me. All right. All right, so is my screen up already?
Yes, it is.
Okay, thank you so much. All right, so welcome to today's webinar. So I'm Sing Chen from Bentley System. So in today's webinar, we'll talk about the PLAXIS, applications, the use of PLAXIS when it comes to excavation and temporary shoring design. So as you might be aware of, so PLAXIS is a software for geotechnical deformation and stability analysis. But in the meantime, so PLAXIS is also able to actually give you the kind of a structural response. All right, so we have a range of structural elements. All right, so for typical geostructures, just like, struct, ground anchors when it comes to excavation. And we have rock bolts, cable elements when it comes to tunnel construction. So there's a range of structural elements, although they are quite simple, they're mostly line element or point element in 2D. And when it comes to 3D, it can be a line element or even a surface element. So in today's context, where we're focusing on the structural element and how we can get the structural response of our temporary shoring, for our excavations. So that's very important. So to begin with, in practice, we offer a wide range of structural elements, and we're gonna look at a few of those that's related to excavation modeling. And so to begin with, in practice, we actually differentiate the behaviors between a thin wall and a thick wall. So for the former, the thickness as well as the geometry effect nearby, are actually negligible. And plate element, if you heard of it, is sufficient to represent the dominant behaviors other than end-bearing. So that's when you emphasize on bending behavior of the retaining wall. So plate is actually the structural element that you would use to model the retaining wall. And for the case of thick wall, we may want to model the real thickness using the volume element with the constitutive soil model parameters. But the drawback of modeling the wall as a volume element is that no structural response will be available or directly available. So there's, however, a trick. All right, so using that, you could actually, introduce a plate element just for the extraction of structural response inside a volume wall. So there are two approaches. These are the two approaches when it comes to modeling the retaining wall. Either you model it as a line without physical thickness, or you model the actual thickness using a volume element. So introducing the dummy beam approach that's related to thick wall modeling. That means now you model the wall as a volume, as a soil clusters. And in this approach, we model the real thickness of the wall as well as its material properties using the relevant constitutive soil model. And in the geometry center, in the center of the wall, so as the image show, we insert a weightless plate element, but of course with some reduced stiffness. It's often in the order of 1,000 times or even 1 million times. And no interface in this case should be applied along this plate element. And after the calculation, we would multiply the structural response, say the bending moment or the forces, by the same factor that we have reduced. Right, so the initial vertical stress in the soil should be subtracted from the actual force of the plate in order to get that genuine actual force of the wall. So the idea is that you insert a dummy beam with reduced properties because your volume wall and its soil property already account for the strength and stiffness of the retaining wall. So now you insert this plate in the center of the volume wall is just for extracting the structural response of the calculation. That means, all right, bending moment, actual forces, or shear force. So the idea of introduce this dummy beam is just for the extraction of structural response. Therefore, you should not actually input the actual property of the retaining wall for this plate. Otherwise, you'll be over accounting for the strength and the stiffness of the wall. Combined. So as you know, the excavation can be stabilized by strut or anchors or even a hybrid system of both. So for the case of a strut, it's the compressive resistance that's being mobilized. While for the anchor element, all right, so and the anchor element in this case is so fit for purpose, it supports the pre-stressing option as well. So as you can see from the image, when half model is considered, we may use the point element, like fix and anchor, together with the definition. That's one of the properties for this fix and anchor by the name of equivalent length and also the orientation vector. So that means although it appears a point in the model, but numerically, the program actually consider this as a half span of the actual, struct element spanning across the entire excavation. So that's the idea. Although it appears a point, but there's some numerical, formulations allows this point to behave like a half span of the struct element. And this is normally relevant when you're doing half model, because when left and right are in perfect symmetry, so you may cut the model into half. All right, so just to save some computational effort. So in this case, the equivalent length of this fix and anchor is normally taken as half of the excavation width, because now you're modeling half of the models. And the vector, all right, should actually be pointing towards the axis of symmetry. So consider your axis of symmetry is the vertical line over the left of these models. So the vector should be pointing towards that direction. And for the case of a tie bed system using anchors or soil nails, the excavation is stabilized by the tensile resistance as well as the bond stresses if the soil nail or grout anchor is being considered. So in that case, you may consider a hybrid system depending on what kind of anchorage is relevant for the problem. So you can, for instance, use a combination of different structural elements to simulate the geotechnical applications of grout anchor. So it comes with two parts. So the free tandem part of the grout anchor. So this part we normally model using the node-to-node anchor structural element from PLAXIS. All right, considering the anchor group spacing and also the main structural behavior of tension, while no interaction with the soil is required for the free tandem part. So basically, you just want to mobilize the tension for the free tandem part of the grout anchor. And the grouted part can be modeled using GeoGrid or embedded beam. And the drawback of using GeoGrid in this case is, however, it presents a rigid connection, with the surrounding soil that does not give a good resolution of the genuine grout and soil interactions. So embedded beam is a preferred choice here. It actually accounts for the relative slipping behaviors between the power and soil. So that's in short, the soil structure interaction, the grout and the soil interaction, those kind of a relative movement and friction bond stresses can be mobilized. If you consider the grout as an embedded beam element. And this is how it looks like for different combination of structural elements used to represent the grout anchor applications. So as you can see, so two different types of structural elements. So the black color is the node-to-node anchor used to represent the free tandem part. So this part we do not expect any interactions along the free tandem length itself, but just the tension at the end point of this element. And for the embedded beam, so we have, a special interface that accounts for the soil structure interactions. All right, so this is the typical combination if you want to model it, this kind of a hybrid reinforcement system. All right, so the figure here shows the distribution of axial force along the free tendon and the grout. So here we see a full transfer of axial force from the node-to-node anchor to the embedded beam element. This is, however, not always the case if you would consider different combination. Let's say you don't want to use embedded beam for the grounded part, but you use geogrid element. So in that case, you will see that part of the actual force actually goes to the soil, which is less realistic. All right, so this is actually the consequences. Whichever tension force mobilized in this part does not 100% being transferred to the grout part at the end. All right, so this part of the force actually transfer to the soil unexpectedly. So that's why we'll actually make use of the node-to-node anchor plus embedded beam element when it comes to this kind of grout anchor applications. So as you can see here, there's no loss of actual force or whatsoever being transferred to the soil. All right, so the application of grout anchor involves some engineering uncertainties. All right, for instance, the size and the bonding between the grout and the soil. Typical application requires a pre-drill of some 10-20 meters to reach out the hard material in order to look for better anchorage. And over such a long span, I mean, certain part of the borehole might very well collapse already and may result in some undersized reinforcement. That means although the grout is intended to have some, 250 diameter, the kind of a grout size, but since the borehole collapses, so you could very well get some undersized, grouting reinforcement. So this is something beyond what PLAXIS could handle. So what happens in PLAXIS is an ideal situation. So everything is in perfect consistencies. So so this is part of the so this is something you need to be aware of. All right, so preferably you have a representative pull-out test in the field. You can use that to calibrate the numerical resistance in PLAXIS. To at least avoid over-prediction of the performance. So if you have a few pull-out tests of the angle in the field, you can as well, model it in PLAXIS and just use it to calibrate, its capacities. So when modeling the grout using embedded beam, you have to define the skin resistance profile, as mentioned, based off a pull-out test from the field. So be aware that the input of skin resistance in this case is in the unit of kilonewton per meter. So in case you have, skin profile in kilopascal, so you need to do a conversion, by taking into account the circumferential length of the grout, right? So in order to arrive at the input value, so the unit actually matters. So it does not take kilopascal, right? But it's a kilonewton per meters, and a simple conversion by taking into account the circumferential length of the grout will actually solve the problem. And soil structure interactions. All right, so by default, structure and soil in contact are rigidly connected to each other. So meaning that share the same degree of freedom in all senses, which is less realistic. As the interface between the soil and structure, to a certain extent, they are weakened and slightly to undergo differential movement in response to that loss of equilibrium. And the interface element, in this case, has two sets of springs in the normal and the shear direction to control the gapping and slipping behaviors. And the interface element is a linear, elastic, perfectly plastic, just like the Mock-Coulomb models, and is governed by the Mock-Coulomb failure criterion as shown in the image here. All right, and also the shear and tensile strength. So by default, these the interface properties, all right, the properties are correlated to the surrounding soil through the R intervalue. So R intervalues is, is the third or fourth tab from your material property for soil. You can actually find this R interparameters. So it has a range from 0 to 1 and is defined in the interface tab sheet. For every soil or interface materials. When R inter equals to 1, the latency psi are equal, for interface and the surrounding soil. While for R inter smaller than 1, the interface, the latency reduces to 0. While most of the interface properties, like cohesion or tangent phi or even tensile capacity, follows a linear correlation to the soil. But it's worth to note that, however, for shear stiffness, it has a quadratic dependency, of the R inter on the soil properties. So that means for R inter value, when you input an R inter value less than 0.5, so there are some consequences. That means the interface and the soil stiffness will start to diverge. So for instance, it might drastically reduce to just 25% of the surrounding soil stiffness, just when you define R inter equal to 0.5. All right, so therefore you may want to refrain from using too low a R inter value after you, acknowledge this kind of consequences. But alternatively, you may also create a separate set of material and assign it to the interface so as to have more control on these interface properties, in which case you want to leave the R inter value to 1 for the interface material to prevent any further reduction of the interface properties. You just define directly what the interface properties are by creating a new soil material. All right, this way you have direct control on the strength, the stiffness of the interface, and you just assign these new materials to the interface, like what you do to the surrounding soil. So here are some reference values for the R inters for different types of soil structure interactions. So basically, the R inter measures the surface or the contact surface roughness between the soil and the structures. The rougher it gets, higher is the R inter, and vice versa. And ultimately, R inter is just an arbitrary value that shouldn't get critical and govern your excavation design. All right, so moving on to the second part. So there are a couple of considerations. When it comes to model this boundary, to the model boundary selection, it depends, for instance, the type of analysis you are doing, the type of behaviors being considered. And in case the geometry and loading is in full symmetry, like as mentioned earlier, you may simulate just half or even quarter of the problems in 3D or 2D. And the guideline going into model boundary selection is that the chosen boundaries should be large enough to accommodate all mechanism development, but not excessively large that would cause additional computational effort with no significant increase in the accuracy. So say, for instance, you wouldn't need a 200-meter wide model just to analyze a 5-meter wide excavation. So for excavation problem, we have a multi-criterion here saying, the model size should be no less than 1.5 times of the wall length or 3 times of the final excavation depth, whichever is larger. And at the base of the model, it's advised to have a stiff material for layer thickness equal to 0.5A. So A is the parameters as shown in the schematic. All right, so it's recommended to have a stiffer layer at the very bottom of your excavation model. All right, so that's equivalent to 0.5 times of the A parameter as shown in the schematic here, just for better control of the upheaving behavior at the excavation bottom. And the hardening soil small strand models, all right, so it's one of the advanced soil model in PLAXIS, actually gives the best resolution by accounting for the small strand stiffness. And ignoring that small strand stiffness, what's the consequences? All right, so it will results in excessive upheaving of your excavation base and also a wider sediment trough behind the wall. So these are the consequences if you ignore the small strand stiffness. And for A for the parameters as shown in the schematic once again. So for A less than 3 times of the D parameters. So the D parameters is your final excavation depth. So when A less than 3D, so significant settlement may be expected, over the upper model corner, and it's more pronounced if you use undrained material. If undrained material is been involved in the modeling. As of the consequences on the structural behavior, so you might have unrealistic heaving of the excavation base, which in turn cause the wall to heave as well. And this can be optimized by introducing stiffer material just right below the excavation. For A parameters less than 2 times of the D parameters, the wall displacement will be influenced by the vertical boundaries. Yet there's no direct evidence that the structural response will be affected though. So these are some of the known consequences, on the model boundary selections in terms of model width and model depth. So as excavation problem, as you know, involves predominantly unloading, but also some shearing and primary loading depending on the stress state and the presence and whether or not you have the reinforcement introduced. All right, like in the excavation or temporary shoring, those are actually kind of a form of a reinforcement. And HS small strand model, as mentioned earlier, is the preferred choice for excavation problems with the features like small strand stiffness and also shear hardening and nonlinear unloading reloading response. So these are the typical features of the hardening small strand soil models, right? So that's quite sought after for modeling unloading problems like excavation. So here is the stress path at different part of the excavation. So if you look at point A behind the wall, all right, so it first undergoes some stress relaxation upon the first excavation. And its stress state transition from the K0 state at rest to some active state and bouncing back towards the passive state upon, further pre-stressing. All right, so depends on the case, or we might also preload the shoring or the prop element in some cases just to remove the slack of those, reinforcement with the wall and the struct or ground anchors. All right, and further excavations. So point B is at the base of the, on the other hand, you undergo similar stress relaxation and it's going towards the passive state. So this is what's going on in a typical excavation problem. So typically you have this kind of activities like remove the soil and you activate the struct of pre-stressing. All right, so these are the general behaviors. All right, if you look at this kind of a stress path. All right, so in this figure here, actually illustrates how different soil behaviors are governed by relevant stiffness parameters for an excavation problem. So here the figure here illustrates how different, right, you have 3 different parameters. All right, so this is relevant for advanced soil models for at least hardening soil. All right. So as you can see here, the soil behavior further away from the center of the problem is actually governed by the small strand stiffness of E0. All right, so this is what we call the small strand stiffness. And the soil behind the wall, all right, in this case, is predominantly subject to horizontal shear and depends on the initial stress state. If the soil is over consolidated, then the behavior at the very beginning will instead be governed by the EUR, which is the elastic stiffness, up to a point when the deviatory loading takes place. All right, that means the shear. All right, then the E50 will get in to actually control the shear deformation. All right, so this is the behaviors of the soil next to the excavation. And also for the soil below the excavation, will undergo this major unloading, as mentioned earlier. So in PLAXIS, unloading, reloading is fully elastic. Therefore, the behavior is governed by the elastic stiffness of EUR. So for excavation problem, mock Coulomb models has the tendency of over-predicting the amount of upheaving at the base and also behind the wall. In the extreme case, you might see, some anomalies. For instance, the excavation widens. That's, a bit counterintuitive. All right, so as you excavate, so the wall should have a tendency of leaning into the excavation. But if, however, you see the wall actually widens, so you should actually review, the setup of the model, your choice of constitutive soil model, and the combination of parameters. Right, so that's the idea. So with advanced soil model like hardening soil model, we'll see quantitatively, some quantitative improvement on the prediction of deformation. And hardening soil small strand models is the preferred choice as mentioned earlier. All right, so if you take into account a kind of a small strand stiffness, or we call it a far field stiffness, all right, so the numerical result will be less sensitive to the model boundary that you have chosen. All right, so that's the idea. All right, so we'll actually go into a demonstration on the fly. So let me open up PLAXIS program. All right, so you are in PLAXIS, by the way. So yeah, let's look at 2D. Just for a quick idea. All right, so in this case, we typically begin from the soil mode. So you see there are 5 modes here. All right, so you can define as many borehole as you want. So each borehole has the layer thickness, number of layers. All right, so you can actually define the number of layers as many as you want from this borehole. So with one borehole, you can actually have as many, layers as you want. All right, so in this case, we, let's go with an arbitrary number of layers. All right. So in this case, if you look at, you are in the soil mode, by the way, if you look at the borehole, right? So this is how it looks like. So over here, you can actually define the material and define the number of layers define the layer thickness. Right, so next we're going to create material. So if you have the material already in place, you can actually assign it to the drag and drop fashions. So let's go by layers. So as soon as you see the color changes, you know that the material assignment has been successful. All right. So this is how you actually create and assign the soil properties, the soil material, to the relevant cluster. All right, so this way we actually finish defining the soil. All right, so as mentioned, so here is the top and bottom coordinates of your layer. So you can actually try to change all these values to achieve a different layer thickness. So in this case, maybe, so let's just go with arbitrary, thickness. All right. So this is how you could actually achieve, typical, borehole layers. So many layers, each layer comes with different thicknesses. Okay, so we're finished with defining the soil. So the next step is to move to structure mode to define the excavation geometry. So in this case, as mentioned, the model boundary is actually, all right, depends on the width and also the depth of the excavations. All right, so in this case, you can actually look at different, combinations of your excavation geometry, where there's a very narrow, the kind of sharp excavation, or some wide excavation, just like that. Right, so in this case, I think it's okay. So, and the type of wall. So likewise, here we use the line element to represent the wall. So you can have different types of wall, like, CPP wall, and Shippa wall, or any other wall diaphragm wall. Depends on how you actually define the properties for the plate elements. So the same line elements, so we can actually, achieve different combination. And you need to define the excavation stages. So how deep you want to excavate by stage, you need to predefine in the geometry mode here in the structure mode. All right, so you can't actually go to the stage construction, all right, to define. All right, you need to predefine those stage. So let's say we want to have a 6 excavation stage. All right. So basically you just create cluster. So using the polygon tool. All right, then you need to specify, all right, by telling the program what are the 4-point coordinates for typical polygons. What are their SY coordinates? So in this case, first excavation, let's say 2 meters. Okay, second excavation, 2 meters. All right, so this is how you could achieve, this kind of all right, so we have an 18-meter wall. So now how deep we're going down, let me check. 10 meters. Right. Okay, so maybe. So then you define the wall, you define the excavation level by stage. Then you need to come up with definition of shoring support or any loading. I mean, if there is. So two types of shoring that's common for excavation: shrug element or tieback. So these are the two typical types. So in this case, for the first excavation, we'll use a shrug element to represent. All right, we just try to mix it up. So as a tieback, we try to alternate this kind of reinforcement just for the sake of illustration. Then we come back again with a shrug element. And once again, there's a tieback. So we'll go back to shrug and finish up. So as part of excavation shoring or prop design, you not just want to, verify different support elements, different sections, but also the position of the prop position. Whether it's a midway down the excavation depth or slightly below, it's going to make a difference. All right. So in this case, we just leave it as default. We place the shrug at the midpoint of the excavation depth. And then you need to choose the element. So what kind of sections? In this case, we use a universal column, so 400 by 400. Then for this one, tieback. All right, so as mentioned, we have control on the prop position. So in this case, we make it a little bit lower. And in this case, maybe extend it slightly longer. And can actually change the kind of inclinations. So the idea is to reach out to competent, geomaterial in order to have the kind of a sufficient anchoring effect. Right, so this is what we normally do for excavation. And likewise for the free tandem part, so we have different strength. All right, so whether it's a thicker, steel tandem parts or slightly, thinner. So it depends on the number, of the wired strength in the free tandem part. All right, so the larger it is, the larger actual tensile capacity, it has. So this is how you actually define it. Right, then for this one, we may as well look at larger sections, sebagai structure. So, for some wide excavation, when you have your structure, spanning over 10, 50 meters. So we typically look at, lay structure, which we combine multiple, section of the same kind to make it a bit bigger sections in order to, have larger buckling capacity. So this is what you normally do. So then for this level, likewise, we could go a little bit lower. All right, and we want to reach up, deeper. Okay, and extend the length of the grout. Right, so this is what you can do. So this is actually what we call the iterative process. And with the program, PLAXIS program, so you can actually use to, verify any design, any combination. So there might exist tons of, combination of design. All right, so the idea is that you could actually verify one at a time, by using PLAXIS. So that's the idea. All right, so in this case, we're using a stronger redundant element. All right, so last session, we fall back to us. Still using lace route. Right. So at this point, we are done with the geometry creation. All right, so what do we have here? We have the soil and the associated soil material assigned. And over in the structure mode, what do you do here? You predefine those excavation volume by thickness and by stages. This you need to predefine, and also the structural element, the position of it, the type of support, right? Whether it's a shrug support or it's a anchor or even soil nail. All right, so all these things you must predefine. So for any soil and structure element you define here, you need to actually do material assignment. That means you need to create this material property for the structure and the soil element and assign it. All right, so then you can call it final and move to mesh to generate a mesh for finite element calculation. Right, so then you go on to define the excavation stages. So in the borehole, you can actually define where the initial water table is for the models. All right, so there's a head field. All right, so for you to quickly define where is the location of the water table in the borehole. So it comes in pretty handy. So in this case, I just leave the water table at the ground, surface. Then realize this is a 2D program. All right, and your spacing of the shoring, all right, is actually defined at its material property levels. So you no longer like 3D program, you can actually define, how much they space, with each other. So in this case, in 2D, the spacing of your shoring, be it on struct or ground anchors, so which is going into your screen, the kind of direction you need to define by its properties. Right, so struct spacing, so in this case, we leave it 7 meters for the first level. And then the tie-back spacing for this one. In this case, just use some arbitrary value, so 1 meter spacing. And also another one, I believe this one is a lay struct, 7 meters. And also the tie-back spacing for this level, 1 meter. Then have this one. All right, so we have finished defining, all the construction stages. So if you drill down one by one, so let's see what we do here. So in this case, we start initial phase, right? So we start with this piece of soil in place. Then we move on to construct the wall just by activate, the plate and the interface element. All right, then we begin our excavation. So we begin with an open excavation without any shoring. All right, so this is to make space or make way for the installation of the first level reinforcement. In this case, we use a struct. Then we move on to the second excavation. Then in this case, we install the reinforcement. In this case, it's not a struct, but it's ground anchor. It comes with the free tandem part and also the ground part. And that excavation, install again the struct, excavate, and there you go. So this is how we reach down to 12 meters in depth through how many stages? 12 stages. So you can actually calculate by stages and get the response in terms of deformation, how the soil deformed, and how your structural element behave throughout the 12 stages, as real as it gets. So this is how you can closely simulate what's happening in the field. So take it to, calculation, just like this. All right, so this is the active task window. So, a bunch of informations here. So from here, you can actually see how the problem converge or diverge. So there's a lot of digits over there, giving you a lot of insights on how the calculation of a particular stages, goes. So you see this kind of excavation problem. So basically we have repetitive activities. So you cut, you activate, and then before you cut again. So this is kind of a cycle, right? So that's very, repetitive in nature. So when you see this kind of a graph, it actually reaches to a parameter called summation MSF in the vertical axis to 1. That means the calculation, finishes. So now we're at stage number 9. We're installing the reinforcement. In this case, it's a tieback. All right. Then we excavate down to minus 10 meters. This is the response. And now we are installing the struct at level 5. And now we're excavating down to the final excavation level. I think it's minus 12 meters. All right, so we are done. Then you can look at the result. Check the calculation result by stages. Right. So, this kind of, as soon as you land in our program, you see this kind of deformed mesh at some exaggerated scale. All right, so what you want to look at, so this is the end of calculation. You can go drill down by phases, what you want to look at. But in this case, we look at the result at the end of calculation. So we look at the structural response, look at the wall. So we select the plate. So what you can get out of the wall, so probably you want to look at the horizontal movement or the wall deflection. So in this case, you have the value here. All right, and the distribution, I may as well open the table. So it has the value, deformation at all points for both walls. You may copy out all this over to Excel spreadsheet program for plotting your own graph. And there is also structure response, like shear force distribution of the wall at the last stage, bending moment, right? And you can actually activate an envelope tool. So envelope has the historical extreme value, be it a maximum or minimum. So this is how you can get out of a PLAXIS calculation, not just on the soil, but also structural response. And then you can use all this for your calculation. Right. Then we can look at, let's say we want to look at the bending moment throughout the stages. Okay, so let's go to the very first stage when you install the wall. Right, so this is very small values. All right, less than 0.1. And as you install the prop, as you excavate, so you see the wall start to respond to the change. All right, so you see a double curvature when you excavate, second excavation stage, down to minus 4 meters. All right, then excavate to 6 meters, 8 meters. So we see how the structural response, actually change with stages. So this is what you can do. You can query or interrogate the results in terms of soil deformation and also structural response, just like that. In this case, you might also look at the earth pressure. All right, so in this case, we want to select the interface element. So here you can see the mobilized earth pressures. So this looks a bit different than what you do with it traditionally, there's a triangular distribution. But as you can see here, so I mean, we're doing nonlinear calculation. So as you can see, those kind of, I mean, mobilized earth pressure is not, I mean, as triangular as what you perceive, I mean, with the traditional way of doing it. All right, so this is based on the actual mobilization of earth pressure, and actually vary by different excavation stages. I can show you, or even different propping stages. All right, so this is unique about finite element calculations. So the mobilized earth pressure is actually the result of calculation. All right, it is not made known upfront. I mean, so this is one of the quantities, I mean, after the calculation that you could get. And what else I want to show? So you're probably interested about the structural response for struct. All right, so this is the values. So in this case, it's been designed as a purely compressive element anchor. So you get the mobilized actual capacity. In this case is 311 for the first level of struct at the end of calculation. Then how about the second one? At the end of calculation, your second level of struct is like this amount. Wow, that's gigantic. That's almost 10 times of your first level. How about the last one? All right, it's more or less. Then what I can get for the, what I call it, the free tandem part of your tieback. All right, you see for the first one, it's very small in tension. And how about the last one? It's not as large, I mean, as the struct element. All right, so this kind of tieback is a bit, I mean, slack. All right. So how about the grounded part? You can also check the grounded part. I mean, you can check the mobilized capacity. So this one is the capacities. So in this case, the ground strength for this one at the end of stage is being mobilized, I mean, about 45%. All right, for this case, then how about other part? So in this case, if we look at the mobilized bond stresses, so in this case, it's more uniformly, I mean, mobilized for the tieback grout at this level at the end of calculation. So these are some of the idea you can get out of calculation. And these are the actual mobilized skin. And you can look at the shear force as well, actual force, bending moment even for the grout. And what else? I think I want to show, I mean, all right, so let's see for an anchor here. All right, so likewise, we can get the soil response just like that. So you're probably interested, I mean, what's the settlement profile? I mean, meters away from the excavation. In this case, we may use the, what we call it, the cross-section tool to just cut an arbitrary cross-sections in the direction you want. All right. We cut along the ground surface. Then we look into quantity, in this case is settlement. All right, so this is settlement profile at the end of the calculation. Then you can actually make use of the cross-sectional, what I call it, the cross-section tool. All right, you select major excavation stages. So this will give you an idea of how the ground settlement profile changes at different excavation stages. You can make use of this tool. You're going to generate a curve just like this. So this is the settlement. Vertical axis is the settlement. And this is your excavation. All right, your excavation width, the left wall, right wall, So this is how the settlement going to be like. So for this curve is excavation stage number 6 is the final excavation. So we have the first excavation, that gives you a pitch settlement around, we call it 27 mm, then second excavation 38 mm, 57, 71, 90, and 105 millimeter at the end of the calculations. And you can also do this. We cut in the vertical way. So this is to understand the horizontal deflection profile, which switch on the S component, which is the horizontal. And I think there's a way of making it move. I think there's a way of making this cross-section move. I need to. Right, so this is something like a live cross-section, you see? So as I move, all right, it actually give me this kind of a close real-time feedback of how the horizontal deflection is going to be like across the entire models. So this is the beauty of a live cross-section tour. All right, so I think with this last frame, I will conclude the presentation. So I'll turn it over to the host. Thank you.
Thank you very much, Mr. Singh Chen, for your detailed and insightful presentation on excavation. We truly appreciate the depth knowledge you have shared with us today. Okay, Bapak dan Ibu, now we will proceed to the Q&A session. If we have any questions, please feel free to type them in the chat box. Mr. Singh Chen, we have questions. You can see the chat box.
Yes.
We have questions from Mr. Wahyu, Mr. Iksan, and Mr. Alex.
Okay, let me go through the question
Nadia.
one by one. All right.
Yeah, one by one, please.
I'm opening the first one. So what was the first one? It's an absence.
Iksan, yeah.
Absence
from Pak
webinar.
Iksan Harsono.
Oh, that is Bu Nasi's message to them. I think the first one would be Muhammad Iksan, Mr. Iksan. In my view, soil parameters inherently.
Okay, let me check.
Yeah.
It's in the chat window, right?
Yes, in the chat window. Probably you scroll down a little bit more after Bu Nasi's messages.
In my view, soil parameters inherently have a relatively high level of uncertainty. Without conducting a sensitive analysis, PLAXIS modeling result might appear precise. Yet they can actually be highly sensitive to small variation in key parameters such as phi prime, elastic modulus, ground condition. What's your opinion on this matter? And has a sensitive analysis been performed in this study to ensure the reliability and robustness of the model result? It's a very good question. So it's actually quite true. So there's no perfect consistency in soil parameters. So the best way is to do a spatial variation, all right, spatial variability of your, parameters like what you're talking about, the cohesion, and phi. So I think there exists a certain, the kind of deviation. So it's a probabilistic, or statistic point of view. So we should do this. So to answer your question, so you should do it. But in this case, since it's, just for illustrations. So I think this is some very, common geological formation. So over the year, we have our confidence on how the range of parameters, is going to be like. So in this case, in part, this is because just an illustration. And to answer your question, yes, so you should do that. So normally, this is how you actually get the characteristic values. based on 95% the kind of a confidence. All right, so once again, it's a statistic point of view. Then you actually incorporate partial factors, all right, to arrive at your design values. So this is what we normally do. So you need a sufficient sample size to get first the characteristic values of those parameters like cohesion, friction angle. All right, then we incorporate partial factors to arrive at the design value. So this is actually a way to go. So I agree with you. Thank you very much. Second question. If we have soil excavation, we use ship pound to show design. Can we use mock Coulomb model in PLAXIS analysis? So you can absolutely, using mock Coulomb model. So the consequences, the downside of mock Coulomb models is getting apparent when you are dealing with soft material and in combination with undrained assumption. So mock Coulomb, the problem is that if the material is hard enough and you can consider it as a drain material, then there's, using mock Coulomb model to represent those materials, there's not much problems. But when it comes to very soft material and in combination with undrained assumption, so mock Coulomb has the tendency of under-predicting the plastic deformations. So like in this case for unloading problem in excavation, so mock Coulomb model does not come with the advanced feature to deal with shear hardening. There's pronounced the shear loading, deviatory loading behavior in excavation problems. So this is one of the downsides. So you might underestimate the plastic deformation. All right, so this is ultimately attribute to the formulation of mock Coulomb, because mock Coulomb model only gets, only generate plastic strength when failure is reached. All right, but if you look at most of the soft material, they are plastic yielding way before failure has been reached. So this kind of, behaviors can only be accounted for if you use advanced soil models like hardening soil model or hardening soil small strength models. All right, so using mock Coulomb or advanced soil model has nothing to do with a ship power wall or it's a CBP power wall. So there's no direct connection, but it's more on the type of soil you're going to deal with. Whether it's a hard soil or soft soil, it can be used, considered as a drain material or undrained material. All right, so I hope that answered the question. Next question. So how to model appropriate water level in this symmetrical model, and any safety factor could be presented from this analysis. All right, so to model the water level in this case, I think we begin off with defining the head values in the borehole. Then for the excavation stages, we set the particular excavation volume to dry. And in combination with a groundwater flow, we actually reach a pore pressure field that is in equilibrium. So in this case, we make use of the groundwater flow option calculation type for pore pressure generation. Then in combination with the soil cluster water condition setting of dry. So this is what we do for each excavation stages. And as for the second question, any safety factor presented shown for this analysis. So in this case, we are not doing safety analysis for this case. All right, a safety phase is normally carried out before this kind of analysis. And that's what we use to determine what is the embedment depth of the wall. All right, so I actually say the safety factor actually come before this. And in the subsequent stage after the current analysis, yes, you can actually do a safety analysis, all right, to get an idea of what the over design factors is, especially you are incorporating FD, the kind of approach, all right, and running a safety analysis will actually get you an idea of how much safety margin you have. Can we modify manually? each stage construction, like for example, additional temporary berm before proceeding to the next stage of construction. As it seems the process is automatic, looks like pattern wizard. How about asymmetrical excavation, like half side have 4 basement while the other half 7? Yes, you can actually, yeah, this one is doable. You can actually have uneven wall length on both sides if you're dealing with, I mean, yeah, it's doable. But like I said, this case is just for illustration. So we did not actually go into the kind of a rigor to model, I mean, 4 basement one side, 7 basement on the other side. But it's definitely doable. So what you do is that you just extend the wall. All right, and you can introduce berm. So in this case, you're no longer doing a rectangular soil cluster like what I did from the demonstration, but you still use the polygon tool to trace out the size of the berm. I think it's a combination of a trapezoid and a rectangular. So this is how you can achieve at the berm. And building near, yes, it is. It's doable. You can have a meter. Or the older version. Still, the older version of PLAXIS, we can freely model it. If anything you can do in the older version of PLAXIS, you can certainly do it better with the current version. So that's my impression. So how to design the soil if condition liquefaction? All right, so in this case, you need to look into some of the advanced soil models. So all right, so this is a static problems, and you're actually talking about liquefaction is a dynamic problem. So in this case, it might involve a material change. That means you pre-create 2 sets of material for the same material. You create 2 material for the same soil. You create the 2 sets of parameters, one for the static calculation, like what we just did, and another set for dynamic calculation. All right, I think there's only a few soil model in PLAXIS is able to get you the kind of a liquefaction potential assessment. Yeah, so you need to pre-create 2 different sets of material and switch material at relevant case, just where like what you would, I mean, model and dynamic earthquake, the kind of problem. How do you change the groundwater level during construction? You can actually look into the cluster water condition tabs. So for each cluster, there are options: global level, cluster, water level, user defined, water condition, dry, interpolate. So these are the options you can explore for every cluster. I mean, at different stage in the water mode. Can PLAXIS be used to analyze pipe filled with water? Yes, but water is, I mean, exists as some point of load. So if you model water inside the pipe, so I mean, in the program, so you'll see external water load adding against the pipe wall. In excavation analysis, the common best practice is to use hardening soil. Hardening soil is more strength with undrained A because excavation is largely unloading stress path dependent problem. However, soil parameters required for undrained A are often difficult to determine reliably. A possible alternative is use hardening with undrained B. The concern is that this option might seem less realistic because it does not represent volumetric hardening and only include shear hardening, and the stress dependency might seem to be limited. Do you have any advice how to select a practical alternative soil model for excavation when undrained A parameters are not available? So undrained A is actually, I mean, all right, so if you are interested in this kind of, I mean, it's a deformation, right? So you need to actually make use of effective stress. I mean, analysis, which is drain or undrained A. So in that case, you need to actually get the cohesion and the kind of effective stress parameters. I understand it might not be straightforward to get because most of the triaxial tests are either doing UU. All right, so you need to have at least a CIU test to actually get the stress path, get the kind of a cubic stress path, and also, I mean, sample test at different stress level to get the kind of CV parameters. All right, and it can be also be empirical. I mean, empirically, so you might have an idea. I mean, for typical materials, so how the range, how the variations is gonna be like. I mean, for either a C cohesion or B, the kind of stuffs. So some people also use, pressure meter test, and CPT test. So there are some correlations out there in the publications can help you. Yeah, but I think going through a CIU test, I think is probably the best way to get confident about, I mean, under an A parameters. All right, otherwise, it'll be your experience call. You're right that undrained B is unrealistic. So not just it lose the hardening, but it also lose the stress dependent stiffness. All right, you lose a lot of beneficial features as advanced soil models. All right, it only ensures that your shear strength is not over predicted. So that's the idea. Second question, if the ground improvement inside excavation, it can be modeled as a low permeability, high stiffness, sometimes use a more Coulomb near impermeable if we want to represent improved zone as a composite surrounding while using effective. So you have in PLAXIS, you have in the old days, yes, you use a more Coulomb undrained B or undrained C, where you directly specify what is the, I mean, the failure strength, like 150. I mean, there's a correlations for this kind of improvement, the stiffness EU and S and CU. All right, so I think in the old days, you can actually incorporate this in more Coulomb undrained B, undrained C. All right, with a direct input of stiffness and the CU. All right, but now there's also other alternatives. You have concrete models. All right, so it can actually give you this kind of, I mean, cement-treated material, cementitious material undergoing strength hardening, tension softening. All right, so that's more relevant for this kind of improvement. You can look at concrete models. So you have more controls on, as compared to a case, you use more Coulomb. So next question is, can current version of PLAXIS be used for water body excavation? Case on for bridge. I don't recall all one. All right, so this part I'm not very water body excavation. So when you remove water, so there's a quick way. So you just set that cluster to dry. So you actually remove the water. All right, I'm not sure if I understand correctly, but to remove water, you simply set the cluster to dry. Yeah, I think it's doable. How to model unbalanced water pressure in water cutoff system? How does PLAXIS 2D handle embedded pounds in plane strength? So unbalanced water in water cutoff system. All right, so there are two ways. So one way is to, you just define the groundwater flow boundary conditions and permeability and let the program run to get you the kind of unbalanced system. So this way it takes care of the pore pressure equilibrium. Another way is to actually make use of the soil cluster water condition settings. You can use different combinations across the model. You have many clusters. You can actually use different combination to achieve the condition of unbalance, of having unbalanced water pressure, like what you described. And how does PLAXIS 2D handle unbalanced panels in plane strand? All right, so there are 3 sets of a spring. We call it special interface that deal with axial loading, and shear loading, and also embedding. So the idea is that embedded beam only has its top point or first point that's directly connected to the soil, while the interaction along its body with the surrounding soil is going through the 3 special interface, all right, that controls axial, shear, or skin, and end bearing. So this is the idea. In stage open cut involving dewatering in each stage, what is the recommended approach to simulate the change of groundwater level in each construction stage? And do you have advice on which calculation type and pore pressure calculation type is best to use? All right, so you actually have to look at it case by case. So in case the geological formation has multiple geomateria that pose a large contrast in material permeability, like you have sand and marine clay together. So in this case, it's very difficult for you to reach a steady state groundwater flow calculation. So in this case, normally we look into a combination of phreatic settings, right? So still, excavated cluster, you use dry settings. Then for the pore pressure distribution, below the excavation level, you have some options like cluster water level for the first cluster right below the excavation level, and interpolate option, right below. All right, so this will help you to actually achieve a pore pressure distribution that is more or less realistic. All right, but it's very difficult for you to get this kind of actual pore pressure, underneath the excavations. All right, so in actual fact, for excavation problem, we have mass well pumping at the excavation base. All right, so you can actually, I feel that in that case, if you're a mix of a sand or less permeable clay together, all right, a groundwater flow calculation might not be relevant, and you want to make use of a combination of phreatic settings, in particular different water condition settings in terms of dry, cluster phreatic level, hat value, user defined option, and most importantly, the interpolate options to arrive at a more or less realistic water level distribution. Yeah. All right, thank you, Mohammed. Okay, how we determine the length and diameter of the bolt rod which need to be installed? All right, so in this case, you might have some prototype in mind already. So in this case, I would say that I need to actually first ensure that my tie bed is long enough to reach down to some strong material. You definitely don't want to terminate your grout in marine clay layer. So the first idea is to come up with the length of your free tendon that's able to reach down to strong geomaterial underneath. All right, so this way you already determine the length. And next is the grout part. So based on, if you don't have sufficient data to back to support you on the property of that, the grouted material layer, so you can actually make use of the SPDN count. So like for bob pound, driven pound, so we have those kind of what we call correlation of SPDN count value, and from SPDN count value, how do you arrive at the skin resistance of the grout? So this one is something you could use, all right, to determine. All right, and there's a limit. when it comes to grout diameter. So there's typically like fall in a typical range, 250 millimeter, 350 millimeter. All right. So you can actually test out. I mean, you can actually model it in PLAXIS and validate against some field pull-out tests, right, to confirm, I mean, the efficacy of the combination in terms of diameter and length. Okay, so regarding my question for composite material, yes, we can consider concrete constitutive model, but for 2D analysis of composite material, certain improvement ratio combining ground improvement with surrounding soil is hard to justify whether the composite material should be modeled considering yes, you are right. In 2D you have the limitation, but in 3D we have full control. So if you have this kind of a JGP column, all right, in 2D it's very difficult for you to actually make it right, because to make it right in 2D, so it might require you to tweak some of the parameters up to a point when it does not seem realistic anymore. So I think for this kind of a ground improvement, when you want to consider, I mean, typical array of JGP column arrangement, whether it's a triangular, rectangular, or hexagonal array, I think the best way is to actually, I mean, use 3D program. And with 2D, what can you do is that you actually model in the axisymmetric mode for the performance of a single circular, I mean, column, or I mean, reinforcement. Yeah, so this is the limitation of 2D program. Yeah, I think you have to, I mean, make use of the 3D program. So that way you can go out there more carefree, all right, to exercise, I mean, your verification on JGP or ground improvement. I agree with you, it's very difficult for you to judge what is the combined property of it. Yeah. I think if you just if just after the deformation of the treated ground, you can actually, I mean, look into Prohibis methods. Prohibis method, the German, I mean, Keller Foundation's in-house design method. Prohibis method, I think there's a way of how you calculate the equivalent stiffness and also the strength of the treated ground. There's the soil combining, yeah, those kind of cementitious materials. So yeah, you actually give you more or less the kind of a deformation settlement behavior. Yeah, and other than that, you need to actually look into 3D program. I mean, with advanced soil model like concrete model. Thank you so much. All right, I think I've go through all the questions.
Xingchen, sorry, there are 2 more questions in the real-time text chat box that I saw. I can't copy it, so I put it in an image here about factor of safety and model boundaries. Would you probably answer these 2 as well?
Stated if there is additional.
I think the second part is more of the sentence.
Heavy. Additional. If how to calculate safety factor. If there's additional heavy. Okay, so construction equipment. So you need to actually model it as a load, line load. I mean, behind the wall, left or right. You can use the line load element, all right, to actually simulate the kind of a heavy element, construction element, and you activate those elements. I mean, before you excavate, yeah, you'll see the difference. Yeah, you'll see probably more active earth pressure being mobilized. Where should the model boundary be located? All right, so the idea is very simple. You need to, I mean, those are rough guidelines. All right, so how to validate? After calculation, you open the output program. All right, you make sure that close to left and right boundary, you have 0 displacement. So that's the sanity check. If your chosen model boundary is large enough or not. You want to see zero or near zero displacement at both left and right of your model boundary. If you look at displacement, and this will give you an idea whether you have chosen, I mean, sufficient width for the boundary. All right, thank you. I think I go through all the questions already.
We see a hand raised by Emmanuel Toga. Is it a question or Mr. Emmanuel? If no, then we hand it over back to Bu Nessie.
Okay, thank you, Mrs. First thing first, introduces myself. My name is Emmanuel. Work at Sinarmas Mining.
Hi.
Thank you for the presentation about PLAXIS. And my question is, PLAXIS analysis result often show smaller deflection than those obtained using the limit equilibrium method. How do we determine the most appropriate safety factor for temporary structure? And the second question is how to calculate the interface factor between the soil and the shorting wall. Are there any recommended values to prevent overly optimistic simulation result? Thank you for the
All right, thank you.
time.
So your first question, you say PLAXIS tends to give you, I mean, a smaller deflection than what you get from limit equilibrium. Is that the question? So which program you are talking about? I mean, limit equilibrium, they give you the deflection that's bigger than what PLAXIS predicts. Did I get you right or not? And to answer your question, so there's no way for you to actually get the R intervalues, all right, for the interface. Like I mentioned, it's an arbitrary properties. So the importance, all right, is to not get that important up to a point when this value actually governs your design. All right, so if you, I mean, in the old days, all right, I think in the PLAXIS manual, when you are not sure, R inter equal to 2/3. All right, so this is quite an arbitrary factor. I think nobody bother to actually calibrate the kind of parameters, but you have direct control on it if you have idea on it. Otherwise, just some arbitrary value will do. Yeah. I hope that
Thank
answers
you,
your question.
Sinchan.
Yep.
Any other questions? You can raise your hand or write down on the chat box. Oh ya, from Pak Winto. Silakan Bapak open mic.
How to conduct stability analysis for deep excavation with retaining wall? I think you just simply create a new phase following any calculation phase that you want to calculate the factor of safety. And you actually give you the stability response.
Baik, apakah ada lagi dari peserta lainnya? Baik, Bapak dan Ibu, apabila sudah tidak ada hal yang ingin ditanyakan, I would like to say thank you very much, Sing Chan. Truly appreciate the depth
Okay.
knowledge you have shared with us today. Thank you so much. Bapak dan Ibu, apabila ada hal-hal yang ingin ditanyakan lebih lanjut setelah webinar ini, silakan Bapak dan Ibu bisa kontak saya, Nessie. Miss Jamie, could you please share your screen?
Okay.
Ya.
Okay.
Ya, jadi nanti kita bisa arrange online session, discussion khusus dengan Bapak dan Ibu apabila diperlukan tema yang khusus terkait PLAXIS. Mengingatkan kembali, telah saya share di chat box, itu ada 2 link absensi. Yang pertama untuk e-certificate dan poin PKB. Bagi peserta yang menginginkan mendapatkan poin PKB dan e-certificate untuk perpanjangan SKK, silakan memberikan investasi sebesar 50.000 ke Bank Mandiri rekening Himpunan Ahli Teknik Tanah Indonesia. Untuk bukti transfernya dapat disampaikan ke Pak Sugino. Nomornya sudah saya sampaikan di kolom chat box. Selanjutnya ada link absensi. Absen yang kedua itu adalah untuk Kurnia Handasa Nevada terkait EVA License PLAXIS. Nantinya EVA License PLAXIS akan kami berikan kepada Bapak dan Ibu selama 30 hari. Full version. Ya. Bapak dan Ibu, Miss Jamie, bisa diklik? Can you click?
Okay, Bu.
This slide?
Before that, Bu, I think Pak Emmanuel has another question. Pak?
Pak Emmanuel? Ya,
He
silakan
said,
Bapak.
Kepada saya, Bu.
he asked if he can continue his question.
Oh yeah, thank you for the time, Miss Jamie and Mr. Okay, my question is continuing my previous question. How large is the deviation between the limit equilibrium method approach in PLAXIS and rock science slide or similar software? Thank you.
Vincent?
But rock science, do you calculate a factor of safety and also the deformation for the excavation? Am I right?
Right.
And which soil model do you use? All right, I think there's a lot of variables. All right, so I cannot comment directly on why, I mean, the value goes higher on one application. So I think I cannot actually, I'm not fully 100%, I mean, I'm not 100% about, I mean, this kind of basis. Do we have the same basis, whether it's an apple to apple, the kind of comparison? So this part, I'm not very sure. So unless you can give me more, I mean, information during this session or after that. So I think it's very difficult for me to comment on question like this. Also, why this value is higher. So my first question is that, are we doing an apple to apple comparison? All right. So based on the information like this, so I do not think I have anything, I mean, to comment on that. So it's very difficult. So unless you want to share more information during this session or after that. Yeah.
So, Pak Emmanuel, if you have any question, you can let Bu Nessie know, and we can have the discussion separately on the question that you have just now, so that we make sure that, like what Sington said, the comparison is more apple to apple.
Okay, thank you, Miss Jamie and Mr. Xiang Chenglin for the answer. It's enough for me. Is about to liquid limit equilibrium is not apple to PLAXIS on similar software? Thank you for the answer.
All right. So when you're talking about limit equilibrium, so which program in rock science are you talking about? RS or slide or which one? I think there are a lot of products, so I'm not sure which one you are comparing. And did you actually do the same example in PLAXIS and you find out things turn out different? All right. So this is something I need to understand. Right, I turn it over to the host.
Mr.
Yep.
Yeah. Thank you, Mr. Sing Jenglin,
Oh, okay,
for the
fine.
answer. Okay.
Terima kasih Pak Immanuel untuk pertanyaannya. Apabila sudah tidak ada pertanyaan lagi dari Bapak dan Ibu, bisa kita akhiri webinar kita pada sore hari ini. Terima kasih banyak Bapak dan Ibu atas antusiasme dan partisipasinya dalam webinar ini. Terima kasih HATTI, mohon maaf atas segala kekurangan. Untuk license, poin SKK, dan kebutuhan software PLAXIS bisa menghubungi saya dan Pak Sukino. Terima kasih banyak. Selamat sore. Wassalamualaikum warahmatullahi wabarakatuh.
Selamat sore, Bu dan lainnya.
Selamat sore.
Selamat sore. Thank you.
Thank you, everyone.
Thank you.